Right? Well, this is remarkable. I said 7.5 minutes, and without a prompt from me, 7.5 minutes have passed, and suddenly everybody's quietened down, right? I thought it would take me at least 3 minutes to get you back into your seats. All right. Right. So what I want to do next is we've, the outcome of the previous discussion is that the generic beast that we're considering is a vector system for vector y, where the rate of change of y is equal to some f of t and y. So, and this is in n dimensions. Now, and so you can see that in some generic sense, you can say that y dot equals to f, right? So f is a kind of velocity field, right, in the space of y, right? So this sits in what is sometimes called the phase space. So the phase space of the differential equation is the space in which the function, in which the dependent variable lives, right? So in this case, it's Rn, for example, or some subset of Rn. Or actually, nothing terrible happens if you make it Cn, complex numbers. That's fine as well. It's called phase space. It's old terminology, right? Same reason why we talk about phases of the moon. Phase of as a state of, right? So it's a space of states of the system, which are defined by particular values of y, right? This then is phase velocity, right? So velocity in phase space. And this, so physically, if this describes laws of motion, right, then y's are velocities and positions, and therefore phase velocities are velocities and accelerations. All right, an acceleration is the velocity at which velocities change, right? So now, naturally, I could ask for whether I could have a Cauchy problem associated with this, which means, can I solve these equations subject to stipulating that y of t naught is equal to some y naught? Okay. Well, thankfully, the solution to the Cauchy problem exists and is unique. Remember, I formulated this for 1D equations already, so it's a non-trivial step to say that that's also true for n equations. Right, so here's a simple version of the existence theorem, existence and uniqueness theorem. So, and here's its precise formulation. So let all functions f of t and y and all their derivatives dfi by dyj for I and j going from 1 to n exist. Exist means they're not infinite, right? And be continuous on some open domain D that's sitting inside Rn plus 1. So Rn plus 1 because y is an n-dimensional thing and the plus 1 comes from time, right? From t, the variable t. Then, first, for any t naught and y naught inside this domain, there exists a time interval delta t such that the Cauchy problem has a solution in the interval I, which is from t naught minus delta t to t naught plus delta t. So it's the same formulation as before. So I can pick any point in the domain where everything is specified and is nice. And what's guaranteed is that I can have a solution in some vicinity of that point in time, right? So I can continue my solution a little bit after and a little bit before. Okay. So and secondly, this solution is unique. So meaning that if I have two solutions in two different intervals, then they will coincide on the intersection of those two intervals. Okay, and this puts us in business in terms of solving nth order differential equations or n-dimensional differential equations, right? So Cauchy problem is a good problem to solve. In fact, it turns out that this theorem can be generalized a bit. You don't actually need, so parenthetically, I'll say to you that it turns out that so the theorem can be made more general, meaning I can weaken its assumptions, right? I don't actually need to assume, it turns out, that the function f has all its derivatives continuous. All you need, in fact, all that's needed of f is a condition which is called Lipschitz continuity. So Lipschitz continuity, it means this. There exists a number in R such that for any points ty1 and ty2 inside our domain, it is the case that f of ty1 minus f of ty2, the norm of that is less than the distance between y1 and y2 times that L. So that's the most general known setup in which you can guarantee existence and uniqueness, right? And so existence and uniqueness are then guaranteed by a theorem known as Picard's theorem. So I won't prove this theorem, but I urge you to read books and educate yourself on this mathematical aspect of it. So I put in a portrait of Picard for you to motivate you to do this. I put in a portrait of Picard into the latest version of the notes. He looks exactly like Hercule Poirot, right? Or rather like David Suchet. But he is a real person, was a real person. So now, okay. So now let me do the following. So this is so this sets us up for further careful study of differential equations in that form. But I think it's probably important to tell you where we're going with this, right? I mean, so what's the outlook? You know, why we're doing all this study and where we're going to end up. So let me give you a kind of an introduction to study of differential equations in phase space. So let's think about this n-dimensional system. So remember, in 1D, I said to you that solving an equation means finding all its integral curves, right? So integral curves were essentially graphs of the solution. When we dealt with the one-dimensional equation, they were in a two-dimensional space, right? Y and t, or y and x, if you like, right? So there was the dependent variable, sorry, the space containing the dependent variable and the independent variable. Well, now integral curves will live in n+1 dimensional space, right? And whenever n is larger than 1, this is problematic because we don't know how to draw in anything except 2D, basically, right? I mean, three-dimensional drawing is probably coming as a piece of technology, but we don't have that yet. And actually, even when you know the nature of our imagination and our comprehension of what's going on is quite limited. We can look at a two-dimensional plot and everything is easy. We can look at a three-dimensional image and we can just about grasp what's going on. And of course, in 4 dimensions, nobody really has any proper intuition. So this is what I was earlier referring to, right? 3 dimensions are challenging, right, to human beings. Another somewhat dispiriting thing is that most of these n-dimensional equations are impossible to solve in quadratures, right? Even the linear ones are very difficult. So you know, if I take, for example, y prime a of x, sorry, y double prime plus a of x plus y prime plus bx of y equals to 0. Second order linear equation, right? Look at this. Let's make z equal to y prime over y. Well, then y prime is equal to zy. Y double prime is equal to zy prime plus z prime y. If I then substitute these into here, let's see what happens. We get zy prime plus z prime y plus a zy plus by equals to 0. But y prime is zy according to that substitution. And then y cancels everywhere, assuming it's not 0. And so I get z prime plus z squared plus a of x z plus b of x equals to 0. And that's a Riccati equation. And Riccati equation, as I told you in the previous hour, is unsolvable in quadratures. So not even a second-order linear equation, generally speaking, can be solved in quadratures, which is terrible, isn't it? So, so what modern humanity does when it's faced with an unsolvable differential equation is typically to stick it into a computer and hope for the best. but as it turns out, if you don't really know what you're doing and if you don't really know what you expect, there isn't actually very much you can get out of a computer, right? A computer is a very powerful tool, but also a very dangerous one if you are not able to assess the results and decide that they are right. This is the same incidentally applies to working on any problem, the solution to which you don't know in advance. Right? It always helps to have some kind of qualitative idea of what should come out. This is how you know whether you are right or not when you've solved something. So, so that means that we need to develop some way of dealing with differential equations that does not rely on simply writing out the solution in quadratures, right? Because otherwise we'll be very limited in what we can do. So, so let's think about how one might do these kinds of things. So first of all, let me make the type of system that I consider slightly less general. So let me consider, instead of that general system which was y dot equals to f of y and t, I want to consider y dot equals to f of y. So what do I mean by this? So here there is no t dependence. So the right-hand side depends only on the state of the system, but not on time. Such systems are sometimes called autonomous. They're called autonomous because if you think of them as a physical system, that says the force on your system depends on where your system is in phase space. But that dependence doesn't change with time, which means there's no external meddling. Right? You kind of you set things up and you let them go. Right? So, well, what one can then do is one can simply, so this f, right, is the velocity field for y, and we can sketch this velocity field in the space of y, right? And this will give us, if we sketch the field lines of this field, meaning sketch the curves such that at every point f is tangent to those curves, right? That will give us the trajectories that the system can follow, right? So these are called phase trajectories, right? So this is the direction field of phase trajectories. Phase trajectories are not the same thing as integral curves. In fact, phase trajectories are actually projections of integral curves onto the space, onto the n-dimensional space of phases. Right? So remember, integral curves are, so if this is y and this is t, integral curves are in this space, right? And phase trajectories are right here. Right, so these are phase trajectories. So this is in Rn plus 1, and this is in Rn. I mean, obviously, there are n dimensions here. So if I learn how to draw a phase portrait of the system, right? So I take this plane, right? And here we have y1, y2, and then y3, and so on, right? And if I learn that my system has certain phase trajectories, then that basically shows me the kinds of things that the system does. If I pick some point and say this is the point at which the system was at some initial time, then I can simply follow this phase trajectory and say that will be what the system does, right? The reason I need the system to be autonomous in order for this to work is because if the system were not autonomous, then this whole plot would change with time all the time, right? Because this plot is simply, the direction field of it is f of y. If f depends only on y, then this is fixed in space and I can just follow trajectories, right? If this also depends on time, as I follow trajectories, the trajectories themselves keep changing. Okay, so and so instead of drawing one phase portrait, you have to draw a phase portrait at every point in time and then follow through them, and that of course is the same as drawing integral curves. Okay, So, well, let me do it. You know, this may sound a little abstract. So let's do an example. So let's go back to the linear pendulum, which I wrote down here. So linear pendulum. So this is a system in 2 dimensions, right? It's a second order system, well, I've already written it for you when I was saying that all the equations, all the differential equations are first order equations. I rewrote this as theta dot equals to omega, omega dot equals to minus omega naught squared theta. Right? So what I'm going to do now is I'm going to make it even simpler and change variables appropriately and simply rewrite this as x dot equals to y and y dot equals to minus x. Right? You can see that this system is the same as this system up to rescaling of time and of the of the variable omega. So so this is the equation of the linear pendulum. Now I can rewrite this slightly differently like this. Right? And so this is my velocity field in phase space. So let's draw this velocity field. What does it look like? So if this is y, and this is x, and what we're trying to draw is vector y minus x. Right? Well, let's draw it in a few places. Right? So when x is equal to 0, then it points like this. Here it points like that. Here it points like that. Here it points like this, and so on, right? So you get the idea, I think. Right, and so if I turn this into a continuous plot, it looks like this. Right, so this is the simplest phase portrait of all time. Right? It's circles. Now, you can, well, actually, it might have been obvious that these are circles. So here, I got these circles as what arises out of things being tangent to this velocity field, right? Now, the way to see that this is a circle, well, one way to see that this is a circle is to note, so this is circle because y minus x is always perpendicular to xy, right? So it's a set of points which, so the, this is y minus x, and this here is xy. So the tangent vector is always perpendicular to the radius vector pointing from the origin, right? And so it is a circle. Another way to see that this is a circle is to remember what the solution was, right? So the solution was that, right? So the solution to the equation is a cosine t plus phi. The y variable is just x dot, right, by our definition. And so this is minus a sine t plus phi. And so x squared plus y squared is manifestly equal to a squared. And this is a family of circles. So this a is the integration constant, and the integration constant tells you where you are on this circle. Right? So if I pick a point on one of these circles, then I will conclude that the pendulum will just go around in these circles. Okay? So there is actually yet another way to see this, right? So this is the first way to see this. This is the second way to see it. The third way to see it is go back to the equation and notice something interesting about this. So we have x dot equals to y, y dot equals to minus x. let's multiply this equation by x, and this equation by y. So what would we get? We would get xx dot equals to yx, and yy dot equals to minus xy. And now let's add these two equations together. And this will tell us xx dot plus yy dot equals to 0. But this we can integrate. It's d by dt of x squared over 2 plus y squared over 2 equals to 0. So we learn that our equation has an energy, right? It has an invariant which stays constant along the trajectory. So E of t, which is equal to x squared over 2 plus y squared over 2 equals to a constant. That's the solution of this equation. And this, of course, again, is an equation for a circle. And so the phase portrait or the phase trajectories of the system are level sets of the system's energy. In other words, if I start oscillating my pendulum at some position that corresponds to a given energy, the energy cannot change, so the pendulum stays on that circle. Okay? Notice that of these three ways of seeing that these trajectories are circles, two do not involve writing down precisely what the solution is. Right? So this is a step towards being able to plot the solution without having to write it down. Okay? So let's now raise our ambitions a bit. And because this may appear to be slightly elementary, so let's become slightly less elementary and look at the nonlinear pendulum. So what's a nonlinear pendulum? Well, that's going back to that equation over there, right? Where instead of small deviations, we consider large deviations of the pendulum from the equilibrium. And so rather than having theta in the right-hand side, we have a sine theta, or in our simple rescaled variables, x dot is equal to y, and y dot is equal to minus sine x. Right? So now let's look at this system of equations. The question is, can I get some idea? Now, this is much harder to solve, right? So if I asked you to write down explicitly a solution to this would be quite a challenge. It is possible to do it. But I doubt you can do it on the back of a post-it note. But it turns out that to plot a phase portrait of this and therefore to understand how the system works is much easier than to actually solve it. Right? So that's a kind of a step in the direction of qualitative thinking about differential equations. And so let me explain to you how to make this step. So I want to use the same insight that I had here at the end, right? That my equation, my system of equations had the property of conserving a certain invariant. Right? Well, you already know that in physics, energy conservation is supreme, right? This is the absolute most important statement. And so, armed with that intuition, we could try and see whether there is an energy for this equation, meaning is there an invariant that's conserved along the trajectories. Well, here's the way to do it. So this here, I want to multiply by sine x, and this here, I want to multiply by y, and see what happens. Well, sine x times x dot is equal to y sine x. That's the first equation. The second equation is y dot is equal to minus y sine x. And again, I can add these two equations together, and then the right-hand side will disappear. So let's do that. Y dot plus sine x dot equals to 0. Well, this is not difficult to integrate, is it? So this is d by dt of y squared over 2 minus cosine x equals to 0. And so there is an energy. I can integrate this equation. So let me integrate it in the following way. I will write the solutions as cosine x plus y squared over 2 equals to a constant, and I wish to add 1 here. I can always add 1 because there's a constant, right? I can just redefine a constant. The reason I want 1 is because I want to point out to you that when x is small, we're back to where we were with the linear pendulum, right? Because so this is approximately x squared over 2 when x is small. This is another parenthetically little lesson in how to solve things. When you generalize something, right? Here we went from linear pendulum to nonlinear pendulum, and you start solving it, it's worth keeping track of whether you can still recover previous results from what you're doing, right? That's a useful reassurance, usually. What this means, right, is that we've integrated our system, right? So the phase trajectories of this system will be level sets of this energy. Actually, let me say that this is a function of x and y. Okay. So phase trajectories are level sets of the energy. Well, you've done your calculus already, right? So you know how to plot level sets of a function, right? How do we plot level sets of a function? Well, typically we find stationary points, right? So-called. Stationary points means stationary points. You've done this already, right? I mean, this must have been just a week ago or 2 weeks ago or something like that, right? So what are the stationary points? The stationary points are points where derivatives are 0, right? And then they're sometimes also called, well, before I say what else they're called, why are stationary points called stationary points? Well, here, this has a very particular meaning. They're called stationary points because if you look at the equations that we had here, notice that I can write the equations as follows. X dot is y, but that is the same as dE by dy. And y dot is minus dE by dx. Right, just check. Right, so y dot is minus sine x, and that's minus the derivative of e with respect to x. So stationary points are actually points where the phase velocity is 0. That's why they're called stationary. Okay, they're sometimes also called fixed points, and also equilibria. Okay, if you are at that point, the velocity taking you away from it is 0, and so that point is a phase trajectory. Right? If you start exactly there, you stay there. Okay? So, well, what are these stationary points? Well, let's see. dE by dy equals to 0 means y is equal to 0. Right? That's one equation. The second equation, dE by dx, is equal to sine x equals to 0. And so this is slightly more complicated. There's a whole bunch of them, right? They're pi n, where n is in is an integer. Okay. So, well, there are two types. So when n is even, then this is actually the same thing as an equilibrium at x equals to 0, right? Or it's identical copies at 2 pi k, right? So what is that equilibrium at x equals to 0? Well, it's this equilibrium. It's a pendulum, and it's simply a pendulum hanging down like that, and maybe oscillating around that, right? So that's this equilibrium. Now, from the point of view of so remember we want level sets of E. Well, at that point, d2E, to know what kind of stationary point a point is, you have to calculate second derivatives, right? Remember that. So d2E by dx squared is equal to a cosine x, and that's equal to 1 at those points. And d2E by dy squared is equal to 1 as well, right? So this is a minimum. And so it's not surprising that the phase portrait around that point is that set of concentric circles, right? The less trivial one is the n equals to odd. Actually, it's as trivial but less familiar. So what kind of equilibrium is that? Well, that's actually the pendulum being upright like this. Right? What does it mean, x equals to pi? Right? It means pendulum standing up like that, right? And can be perturbed from that position. And let's see what happens if it is perturbed from that position. Well, what kind of point is that? Well, d2E by dx squared is now equal to -1 at that place. And d2E by dy squared is equal to 1 again. So this is a saddle point. Now, in order to see what that means and what kind of phase portrait we're dealing with, we should look at the pendulum in its vicinity. Remember, you can, so I linearized this around 0 and got myself a standard harmonic oscillator, but I can also linearize this around pi, right? So let's do that. So let's consider small deviations from this equilibrium. What does that mean? It means that I say that x is pi plus some small delta x, and y is 0 plus some small delta y. And now I take these and plug them in here and expand. What does that give me? Gives me delta x dot, right, is equal to delta y, and delta y dot is equal to minus sine x of pi plus delta x, right? That's just delta x, right? So this is minus sine of pi plus delta x, at delta x being small. Okay? So this is a different system from the linear from the system over there, right? The velocity vector of this system is now delta y, delta x. Let's see if we can plot such a velocity. So this is delta y. This is delta x. What does it do? Well, it does things like this. Right? This kind of thing. So what are the levels as well? You can draw a few of these arrows and try to draw trajectories through it, but an even more rigorous way of doing this is looking at what the energy looks like. So the energy is 1 minus cosine of pi plus delta x plus delta y squared over 2. So if I expand this, what I'm going to get is 2 minus delta x squared plus delta y squared over 2. And the trajectories must be level sets of this. Well, this is a bunch of hyperbole. So let me try to draw the trajectories now. Delta y, delta x. So let me draw them, and then you can decide whether you believe me. So this is the equilibrium point. And then these go in, and then they go like that. Okay? And so on. Depending on the value of constants, you can be in different places in this plot. So, okay, well, let's see if I can combine all that and construct myself a full face portrait of a pendulum. So let's see. So remember, we had equilibria at 0, at pi, at 2 pi, at 3 pi, and so on. And here, minus pi, minus 2 pi, minus 3 pi, and so on. And at even places, we've got little circles, right? So this is what the face portraits look like. And at odd places, we have families of hyperbole. And so on, right? And maybe here as well. And all we now need to connect all this, well, right, so there's our face portrait. And we can put arrows on this, right? So they go like this, these things. Like that, and like that, and so on. Now, what does this tell us? Well, this is the qualitative solution of the nonlinear oscillator, right? What does it tell us? It tells us that in the vicinity of the downwards pointing equilibria, the pendulum will oscillate, right? It'll do this. When it's really, really close, it'll just oscillate as a simple harmonic oscillator, so those things are circles. As you go away, they become these elliptical shapes, right? But they're still oscillations. And then at some point, it gets to here, right? There is this special curve, right? That curve is, well, what is it? What's the value of energy at that curve? Well, it's the value of energy at the saddle point, right? Which means this is energy equals to 2 surface, right? So this is this curve, which separates this behavior from this behavior, is called the separatrix. And so if you're inside this curve, the pendulum will oscillate. The trajectories are closed. If you're outside there, the trajectories are open, which means the pendulum will do this. Well, right? It'll just rotate. Right? Its angle keeps going up. Right? And it can rotate in either direction. So it can either go like that or like that, and that corresponds to this trajectory or this trajectory, which is in the opposite direction. Right? So that's what a pendulum looks like. Well, let's do one more nugget, which shows you how now, this is still entirely solvable analytically, as it turns out, right? You can actually work out explicit expressions for all these curves that are, they're not particularly simple to work out, but they exist. But what you see here is that you don't actually need to work them out to have a pretty damn good description of what's going on, right? And then your solution of Cauchy problem for this is to pick a point here and say, if I start over here, then the pendulum will do this. If I start over there, then the pendulum will do that. And obviously, an interesting region of this is close to the separatrix, right? Because if you're just on one side and just on the other side, the qualitative behavior changes, right? You go from a closed trajectory to an open trajectory. So let's complicate the problem a little bit more. And let's say, well, what if the pendulum has friction, right? So remember, the pendulum in its original physical form, right? The equation was this. Theta double dot is equal to omega naught squared sine theta. What is friction? Friction is a force that slows things down and is proportional to velocity, right? So friction mathematically must look like this. If things don't move, there is no friction. So again, I can get rid of omega naught and so on and rewrite my system as x dot equals to y and y dot equals to minus sine x minus gamma y, right? So this is my new system that I would like to think about, right? So this is pendulum with friction. Well, let's see what happens to energy first. Right? So to get energy, we need to multiply the first equation by sine x and the second equation by y. Well, actually, I'll do it slightly differently. I'll say energy is 1 minus cosine x plus y squared over 2, and I will simply ask how energy changes along the trajectory of the pendulum. Well, this is dE by dx times x dot plus dE by dy times y dot, and x dot is equal to y, and y dot is equal to minus sine x minus gamma y. dE by dx is equal to sine x, and dE by dy is equal to y. And so sine x times y cancels with y times minus sine x, right? And so what you're left with is minus gamma times y squared. So entirely unsurprisingly, the energy of a pendulum has a negative derivative if the pendulum has friction. So, our new phase portrait must include trajectories such that along the trajectory, the energy has to decrease, right? They no longer sit on contours of constant energy, but the energy now has to go down along the trajectory. If we want to get some idea of how this would happen, let's for example look around the fixed point at 0. So consider again x much smaller than 1. well, then our equation is x dot equals to y, and y dot equals to minus x minus gamma y. Right? So how do we plot a radius vector of this? Well, sorry, how do we plot phase trajectories of this? Well, the velocity, the phase velocity field, so phase velocity of this is y minus x minus gamma y. Let's see what angle it makes with the radius vector, x, y. Well, this is equal to minus gamma y squared, and this is less than 0. Right? So the trajectories are no longer circles. Right? The radius vector is no longer perpendicular to the phase velocity. In fact, it has a the dot product is negative. So if you now try to plot these trajectories, well, they will look like this. So this is y, this is x, and so remember previously it was just y minus x. So this would point this way, right? But now the angle is not 90 degrees anymore. It's actually, it has a negative cosine, so it's a larger angle like this, right? So it used to be 90 degrees, now it's pointing downwards. And here this is pointing like that. Here this is pointing like that. Here this is pointing like this, and so on. So what kind of trajectory can we plot for which this is the direction field? Well, it's like this, isn't it? Right? It's an inward going spiral. Right? So things spiral in. Well, let's see if I can modify this plot in such a way as to take account of this. This is a bit of a fit of plotting, I'm afraid. So all these, maybe I'll try to do this on a separate board. So, no, actually, I'll modify this one. Otherwise, I'll screw up. I'm sorry. So all these circles now turn into the inward-going spirals. This, incidentally, is in line with the requirement that energy has to keep going down, right? So the level sets of energy are the circles, and as you go close to the center, the energy goes down and down and down, right? So all these trajectories become spirals like this. Actually, I have colored chalk, don't I? Good. So they go like this now, right? So they go like that, right? So they spiral in. Now, the same will be true about the separatrices, right? So if I'm moving down the separatrix, friction constantly pushes me down towards equilibrium, right? So what will happen to this separatrix? It will also spiral in like that, right? But what will happen to an open trajectory that's very close to the separatrix? Well, friction keeps pushing that down as well, right? So actually, the open trajectory can join the separatrix like this. So we now have a thing like this and going inwards. And now I can try to do the same thing elsewhere, right? So it'll go like that and like this inwards, and there I will go like that, and let's see, down to the separatrix and then inwards again. And something similar on this side. Don't know. Like that. Inwards, and anyway, it becomes a mess, but that's you get the idea. All right? So what does this say physically about the pendulum? Well, it basically says that if you have, so if you're close to the stable equilibrium here, right, what the pendulum will do is it'll just go, right? So now, if you give it a strong kick, it still has an open trajectory which can keep going for a while, but friction will eventually get the better of it, right? So it'll go, okay. So that's the phase portrait of a, what you're now looking at is a generic and probably most famous example of a dissipative system, right? A system which doesn't conserve energy. And again, if we think about the Cauchy problem for this pendulum, short of actually writing down the solution explicitly, which we can't do for this case, what can I say about it? Well, I can say qualitative things about it. I can say if I start with energy less than 2, which means inside the separatrix, then I will have a sequence of damped oscillations eventually leading me into the equilibrium. If I start at energy larger than 2, which corresponds to open trajectories, I will have a few revolutions like this, which will eventually damp down to oscillations and die down. Okay, so, and that's a qualitative description of it. It turns out that you don't actually need to study every single point in phase space. You don't actually need a formula. In fact, if I wrote down an explicit formula, even if I had it for these solutions, you'd look at it and you'll be none the wiser. But when you're looking at a plot like this, you can, well, at least with a trained eye, say very quickly, okay, this is what the system does. That's the basic story. At this point, you can take your oscillator and stick it into a computer and solve it and see whether your computer will give you a solution that's in line with these expectations. Right? So that's the story. So we'll go back to formal study of linear systems next Monday.